For the remainder of the video, we will look at stereoisomeric relationships, which is diastereomers and enantiomers, and we'll look at that with a few examples, again, you tying the whole thing together. So the only way to identify if a diastereomer or enantiomeric pair is present is by determining the absolute configuration at each center and comparing what you get from that situation. So here in A, we have to identify as this chiral. Well, if we look at this position, we have a carbon that's bound to this group. This whole group containing the chlorine is different than the CH3 here, the methyl group, and the bromine and a hydrogen is a dash, so we know that this is chiral. Same argument here, we know that this group is different, so as well it is chiral. So now if we look at this carbon for priority, we know that this bromine is the highest priority. Then we have a carbon bound to a chlorine and a CH3. So the carbon bound to a chlorine is higher priority. So this whole group down here to the right is 2. This group is 3. So that looks like R. It looks like R. The hydrogen is in the back, so it is R. We know that this position is R at the bromine. Then if we look at the carbon with the chlorine would be highest priority. This whole group would be 2 because it has the bromine that's different than the methyl, and then this is 3. So 1, 2, 3, that looks like R, but the hydrogen is in the front, so it's actually S. So looks like R, but the hydrogen is in the front, so it's actually S. So this guy is RS. Then if we look here, the bromine is in the exact same position. All of this is exactly the same, so we know that this one is R for this position. Now if we look at this chlorine, we know that we have switched the orientation of the chlorine from dashed to wedged, so we know that that will also flip the configuration of that chiral center. So this goes from S to R, but we can check if you want. So this is 1, this whole group is 2, this group is 3. That looks like R, and it is R because the hydrogen's in the back. So now we compare these two. This has 2 or more chiral centers. One of them is different, so these are diastereomers from our definition that I started in the video. Okay? Moving on to our next example. Here we have very similar structure. In fact, it is identical here as this one. So we know that this is RR, but we will check. So we have bromine. This is 2. This is 3. That looks like R. The hydrogen is in the back, so it is R. If we look at this one, we have 1, 2, 3. This whole group is 2, so that looks like R. It is R because the hydrogen's in the back. Now we know that these both have switched, so this has to be S and S because we've switched from a wedge to a dash on both of these. So again, 1, 2, 3, that looks like R, but the hydrogen is in the front, so we have to switch it to S. So that's why it's S. And then 1, 2, 3, this again looks like R, but the hydrogen is in the front, so we have to switch it to S. So we get these configurations. And now these are enantiomers because the configuration at all centers has switched. Okay, so moving to the next one, next set of questions. Here we have what appears to be enantiomers. So as you do these enough, you'll quickly see the relationship. So if this is a wedge and this is a dash, you would say that those configurations would be different. But this is a trick question, because you have to assess all the time, is this chiral? So if we look at this position, it's suggesting that it's chiral, right? Like I've said multiple times, we have a wedge, that always suggests chirality. But if we look here, we have the CH3 and a hydrogen, those are different. Then we have a CH2 and a CH2, CH2 and a CH2, and then a CH2. We're at the same position. There's a plane of symmetry across this dashed line that I have here. So this is, in fact, achiral because these groups are the same. So this is achiral as well. So there is no stereoisomeric relationship. This is simply achiral. So these are identical. Or you could say that they're conformational isomers, but those are simply isomers that have a bond that can rotate like this one, and then if you look at the molecule at a very specific point in time, a specific snapshot, the position and the rotation may be different, but that doesn't make them different molecules. They're simply identical and will have the identical properties. Okay, let's move to the last one here. So this is again assessing our Fisher projections. So this one won't be as easy to assess. You will have to determine the absolute stereochemistry at each position, the absolute configuration, to know if what the relationship that these have. So if we look at this carbon, we know that this is chiral because we have chlorine, CH3, hydrogen, and then this group, which is not the same as anything else. So that's chiral. Same for this carbon down here. So this chlorine has the highest priority. Then this whole group here is second priority because we have a carbon bound to a bromine, which is heavier than just a CH3. So this is 2. And then the CH3 is the third group. So this looks like R. And the hydrogen is on the vertical, which as I've shown before is, I'll bring it back up, in our Fisher, vertical is dashed and horizontal is wedged. So because it's on the vertical, it is actually R. So this top one is R. Okay. Now if we have to ignore this 2 here, and we have a bromine, that's highest priority. And then we have this whole group, which is a carbon bound to a chlorine and a CH3, and then a CH3. So this group is the 2 up here. I'll just cross this out because we already used it. And then this is 3. So this 1, 2, 3, that looks like S, but the hydrogen is on the horizontal, so we have to switch it to R. So this is actually R. Okay. Hopefully this is making sense. Let's do the next one. So here, it's the exact same molecule except for the slight difference in we've switched this hydrogen and this chlorine and the CH3. So here we have a chlorine that's highest priority. This whole group is 2. This group is 3. Again, we just assessed them, so the assessment is rather quick now. 1, 2, 3, that looks like R. The hydrogen is on the front, so we have to switch it. So it looks like R. We'll just say look R. And the wedge, this hydrogen is a wedge. It's on the horizontal, so it's actually S. Okay. Now if we look at this position, we have a bromine, and then this whole group is 2. I'll just use this 2 because we know that the chlorine, carbon bound to the chlorine is heavier than the CH3. So this is 2, this is 3. So that looks like R. And the hydrogen is a wedge, so it's actually S. So these are also a pair of enantiomers. And if you look at this closely, you can tell that the only difference between these is that we switch the hydrogen and the CH3, hydrogen and the CH3. Whenever you do that, you just switch 2 groups, you always flip the chirality. You always flip the absolute configuration from R to S. So by doing this, if you can recognize that quickly, and you definitely got the configuration correct on this one, the original molecule, then you can know right away that this is S. You could do the same thing here. We switch the hydrogen and the bromine. Whenever you switch just 2 substituents, it switches the configuration. So this is also S. So you can use that as a shortcut, but you have to make sure that whatever you're comparing to is correct. Otherwise, you can propagate error and get a lot more stuff wrong than if you just assessed it individually each time. So I encourage you to do that. But as you do this enough, you can start to use some of these shortcuts and get this done a little bit more quickly. All right, so this is the last example I will work for this video. So this one is especially challenging because we're comparing a Fisher projection to a normal skeletal structure. So it adds a little bit of ambiguity, but all the assignments are still the same. So first we have to assess where is our chiral center. We know it has to be this carbon because this carbon is bound to a chlorine, bromine, methyl group, and hydrogen. Those are all different, and because of that, this is our chiral center. So then, using our Kohn-Ingold Prelog rules, we determine which atom is the highest priority. Bromine has the highest atomic number and the highest mass, so this will be priority 1. Chlorine is second, so priority 2, and the carbon, the methyl group, will be priority 3, again from our Kohn-Ingold Prelog rules. So now if we look at that, that appears to be going counterclockwise, so S, it looks like S, and the hydrogen is on the horizontal, and if we recall from our Fisher projection stuff, we know that the horizontal are wedges, so that means the hydrogen is in the front, so we have to flip this. So hydrogen is wedge, so we have to flip to R. So this is in fact the R stereoisomer of this molecule. Okay, now if we look at the skeletal structure, again, bromine is the highest priority, then chlorine, then the methyl group. So that's 1, 2, 3. That looks like R. So again, looks like R, because it's going, it's going clockwise like this. So because of that, then we look at the hydrogen. So the hydrogen is in the front. So again, we have to flip this to S again, because the hydrogen is a wedge. So we flip to S. So this is actually the S isomer, stereoisomer. So let me redraw this, just because it got a little busy up there. Okay, and then here. Okay, so we determined that this center was R and this center was S. So those are opposite configurations. So we know that this pair is a pair of enantiomers because the only chiral center that they have in the molecule is inverted in terms of absolute configuration, and therefore it must be a pair of enantiomers. So that is all I have for this video. If you found it useful, please leave a like and subscribe to the channel for more content like this. If you have a topic idea, please leave it in the comment section below and I'll happily get to it as quickly as I can. So I hope you all have a good day and I'll see you in the next video.